In the next section, I want to look at lower bounds. So these are mathematical proofs that certain qualities of these codes are not possible. And we will see that in this case, in some scenarios, we can reach these lower bounds with concrete constructions for codes. In other scenarios, it's quite open and it's still, I mean, a research question if it's possible to reach these lower bounds or not. And if it's possible, how? But let's first see what is not possible. And for that, we have to take a step back and formalize the question a little bit. Every lower bound needs a specific scenario in which it holds. And the same is true in this case. The model here is we want to send a message. So it's just a sequence of bits. Remember the 0, 1 to the star, that means a string of arbitrary length. I want to send this over some communication channel. The model for the channel is it can flip a bit, but no other errors occur. Instead of sending the original string, we're allowed to change it and basically send something entirely different. We send a message C instead of S, where the encoder produces C from S, and the receiver hopefully gets S back from C. But of course, what the decoder receives is not the same C as we put in at the sender side, because the channel might twist some bits. We'll restrict our attention here to block codes. And that simply means we break up the message into blocks of a fixed number of bits. I don't think this is a very severe restriction, but it makes the model more concrete. So the parameters that you should keep in mind, these will occur several times on the next slides, is k for the message length. So k is the number of bits you want to send, and n is the number of bits you actually do send over the channel. So that's the length of the message. We already argued that we probably need more bits in the sending part than we really want to have in the message. And yeah, so all the analysis and all the codes that I know of, okay, I'll take that back. All the codes that we look at are blockwise. There are other codes, but they're not so fundamentally different that I want to extend the model. And the lower bounds are much cleaner for this one too. Remember, in principle, any number between no and all bits can be flipped. We won't get much into the probabilities of these things happening. If you want, we can put a certain probability to each bit flip and assume they're all independent and happening with the same probability. We won't get into the probability side of things. We'll just ask, what types of errors can we tolerate? How many flips can we detect reliably? And how many flip bits can we correct without retransmitting the message? Okay, that's the two concrete questions. And so correct here always means I want to get the exact same message back. And we'll ask how many bits can be flipped before that's no longer possible. Now, if I gave you this question to ponder a bit, you would probably come up relatively quickly with the idea that these code words, what I send over the channel, there are only 2 to the k different messages, and each of these messages is somehow turned into a code, into what I send over the channel. So I have 2 to the n bits, but only 2 to the k different messages. So there's a smaller set of messages. And okay, did I call these block codes or just codes? C doesn't have any name. Just C of M. Let's call it just the code words then. I have a much smaller universe of messages, and every message here is mapped to some code word here. But it means there's there are many code words left after I assign code words to all the messages. That's the whole idea of having redundancy. So what we definitely don't want is 2 mapping to the same that cannot possibly work for decoding it. Right? If you have two things mapped to the same thing, you can't invert it with a function. So this is not allowed. So what we call this mathematically is an injective function from the set of messages to the set of code words. And that's the function C that the encoder uses. And then on the right-hand side, if I take all of these together where they point, so this should really go somewhere else, right? If I take all those, then I get a certain subset of these code words. And that's this set calligraphic C. That's all the code words I can get if I put in all the messages. And that's not all possible code words. More specifically here, this is spelled out again. I think I said this already. In this model, we can make the decoder conceptually very simple. And for the lower bounds, that's good enough for sure. We could say if I receive a code word, if I receive any n-bit string, I find the closest code word. And that code word stands for some message, and that's the message I output. Okay? And with that convention, a key property of a code is this distance of the code. So we look at all those code words, and they live in this space of n long bit vectors. And then I take the smallest distance between any of these. And the distance is the Hamming distance. Remember, we've talked about that in Unit 6. That's just the number of positions where the two strings differ. So we ask, for any pair of code words, how many bits do you have that are not in common? And then we take the smallest of these numbers over all pairs of code words. So you can imagine you put a ball around each of these code words of size d. And if you do that, these balls are not allowed to overlap. And for some pair, they will touch, but they're not allowed to overlap. I should say this is d half, right? If they are not supposed to overlap. The other formulation is, if it's size d, then no code word should be contained in a ball. I think the picture with d half is what we'll need later, so let's use that. And you can draw some immediate conclusions from this. If the distance of a code is d, the best thing we can hope for is correcting d-1 errors. Because if I have two code words that are at distance d, then I could have a message that gives me one code word, I flip d bits, and I end up with a different code word. Well, then that other different code word is indistinguishable from what I would have gotten if I started with the other message. So I can't distinguish those two cases anymore. So I definitely need distance d if I want to detect d-1 bits of error. If you want to turn it the other way around, right? Then if you want to detect k-bit flips, you need at least k+1 as the code distance. And similarly, if you want to correct things, then think about this decoder. It finds the closest code word. So the worst case here is you have some message that's here, and you have some code words. And they're at equal distance from the message. So the decoder has to pick one of the two. So say it maps the message to this one. Now, that will correct some number of errors. But at the point where this message is at the same distance from these two code words. It could have been either of the two. So we have to pick a code distance that's big enough so that this never happens, that every point in this space of possible received n-bit strings is closest to one of the code words. And then again, this is the picture of the balls from before. If you draw these balls around all the code words, and you make sure that each point in the space is closest to one of those code words, then the radius of these balls, that gives you the number of bits you can correct. Because whenever you have something that's just so many bits away from a code word, you can find a unique code word that it is mapped to. And so if the code has distance d, the best you can do is require d minus 1/2 rounding down. Then if the code has distance d, the balls never touch if you take radius d minus 1/2. Okay? So maybe I can add this to the picture. If the distance between those two is d, then the safe balls end here. So we have to exclude the case that the message can be at equal distance. We go one smaller, then we have balls that don't overlap, and every message is mapped to a unique code word. Now, this doesn't say that this is possible. It's just if you want to correct so many bits, you will need a certain radius. You will need a certain code distance. Based on these ideas, we can prove two lower bounds. And the first one is called the singleton bound. I think these lower bounds are a bit more concrete to understand than the previous slide. What this bound says is that 2 to the k must be smaller than 2 to the n minus d minus 1 if you want to correct d bit. So if you have what is d here? It's the distance of the code. These are bounds that say if you want a code with a certain distance, then how much redundancy do you have to add to your message? So the way to read these is the second part. That's the part that we will prove. And if you take this inequality, take the logarithm on both sides and rearrange, you get the right-hand side. What it says is if you have messages of length k, and you want a code of distance d, then you definitely need to put the message size to k plus d minus 1. And the reason for this inequality is we have 2 to the k code words. These are bit strings of length n. So suppose I write them all down. And for each pair of these, there must be, say, when we have distance 3, for each pair of these, there must be 3 positions where they differ. That's the definition of the code distance. If I take any pair of code words, there's at least 3 positions where they don't agree. And so this is true for all of them. We don't know which positions these are, and they might differ, and this is also true for the first and third and so on. What the singleton bound now says, the proof says, if we delete the first d minus 1 of these bits, So you get rid of those. That leaves you with code words that are not as long. They only have n minus d plus 1 bits. But definitely they also all still differ, because every pair of these, they must still have a position where they don't agree that is not among the first d minus 1, just because there must be d positions and we only remove d minus 1 of the coordinates. So we went from having code words that are at Hamming distance at least d to shorter strings about which we only know that they're all different. But if they're all different, we know that we can only have 2 to the n minus d minus 1 of them. That's the length, and the remaining length of this is n minus d minus 1. And if I take 2 to the length, that's the number of such bit strings. So there's no way I can squeeze in more code words of length n than this. And if my message length is k, that says I have 2 to the k different messages, I need at least 1 code word per message. Okay? So the number of code words must be bigger than the number of messages, otherwise I lose the injectivity. So that means this needs to be true. So it's a way, if you start with a certain message length and you want a certain code distance, you need to add at least so many bits. The singleton bound is not usually achievable. So this is a true lower bound. You need at least that many extra bits, but you usually need more than that. There's a second bound, the Hamming bound, that is often a bit, is a second bound is often a bit more useful in terms of giving stricter results. Unfortunately, the inequality we prove is a little more complicated, and so it doesn't have a very nice way to translate into an inequality for n. The only thing you can do, if you have a message length k that you would like to support, and you have a code distance d that you would like to achieve, then you can guess an n, plug it in, and if it doesn't fulfill this inequality, you know it's not possible. Okay, that's the way to use this. Maybe I should put this here so you know k and d. That's what you want from your application. Then you guess an n. Then the bound tells you if it's at all thinkable. And the way to read this potentially possible is, if the bound says it's impossible, it is impossible. If the bound says it is not impossible, it might still be impossible. It might not be something that this bound shows to be impossible. How can we prove this bound? The argument will be similar. We want to argue that if you have a certain code distance, there's not more code words that you can squeeze into the space than a certain number. And that number has to be at least as big as the number of messages. Otherwise, you lose injectivity again. This time we look at balls around bit strings, same idea as before. So we use sets of bit strings that have a Hamming distance at most a certain number from a code word. And we will count all those, and the distance that we use is t, d minus 1/2. That's exactly the distance I argued before. If you have some string that's at this distance at most t from a code word in a code of distance d, you can map it uniquely to that code word. What that means is, if you take all those balls for each of the code words, you take each code word, put the ball around it of distance t, then all those balls don't overlap. There's no bit string that belongs to 2 balls. And that means if I take the size of these balls times the number of balls I need, the number of messages I have to represent, I only count each bit vector once. And I only have 2 to the n. So if what I require the number of balls times the size of the ball, if that's more than there are bit strings in my universe, I'm out of luck. Okay? That's the idea behind this. So what's left is to count these bit strings of a certain distance. And that comes down to this formula. So we have a code word. And then we can look at different distances. For distance 0, there's only exactly this code word itself, right? For distance 1, I can choose exactly one position where I flip a bit. So I have, if that code word has length n, I have n choices to flip a bit. And in general, if I have d equals f, I have to pick f positions out of n to flip. And that's counted by these binomial coefficients. And choose f. That's exactly the number of subsets of size f out of an n-element set. If you're rusty in your combinatorics, we don't really need this here, so you can just use this as a magic formula that Wolfram Alpha can evaluate for you. It's called the binomial coefficient. If you have seen this, I think most of you will have seen this at some stage, then you might remember. And so what this sum here does is just summing up all the vectors of a certain length, of a certain distance. You start with distance 0 and you go up to this distance t, and you sum up how many choices you have to flip away from your code word. Okay? So that's where this inequality comes from. 2 to the k times the ball size times this must be less than 2 to the n, and you just rearrange, then you get the Hamming bound. So again, let me repeat this part here. For both of these bounds, the way you use them is you have to fix the message length and you have to fix the distance of the code that you want. And remember, if you want to correct d-1 bits, if you want to detect d-1 bit flips, you need distance d. If you want to correct d-1 half rounded down bits, you need at least distance d. So if you know you want to correct 3-bit errors, you can work out what the minimum distance is like. So these bounds, by plugging in all these values, can tell you if that's at all thinkable or not.